Hi friends, today I'm going to discuss about the similarities between the model and prototype. So for the definition of model and the difference between the model and the prototype, please uh, see my last presentation where I have explained in detail about the model and prototype. In today's session, we are going to discuss about the similitudes or similarities between the model and prototype. That is, similitudes in fluid mechanics may be defined as the similarities between the model and its prototype in every aspects. What is the meaning of every aspects? Every aspects means there exists a similarity between the model and prototype in three terms. That is, first one is the geometric similarity, second one is the kinematic similarity, third one is the dynamic similarity. Let us discuss one by one these similarities. So first one is the geometric similarity. There exists a geometric similarity between the prototype and model if the ratio of the corresponding linear dimensions should be equal. Ratio of a corresponding dimensions should be equal. For example, this is the prototype and this is the model. LP is the linear dimension of the prototype. Corresponding linear dimension of the model is LM. In the same manner, the breadth of the prototype is, let us say, BP. Corresponding dimension in model is BM. Then, if it is a geometric similarity, then the ratio LP by LM should be equal to the ratio of BP by BM. That is, here it is shown. LP by LM should be equal to BP by BM. That is called as the geometric similarity exists between the model and prototype. And next, coming to the kinematic similarity. When do we say that kinematic similarity exists between the model and prototype? When the corresponding ratios of the velocity and the acceleration at corresponding points in the model, at corresponding points in the prototypes are same. That is, the ratios must be same. For example, you take this is the prototype and this is the model, and these are the 3 points, 1, 2, 3 points in the prototype. These are the corresponding points in the model. Then the VP1, that is ratio of velocity at point 1 in the prototype, that is VP1 should be divided by VM1, that is the velocity at point 1 model, that is VP1 divided by VM1 should be equal to the VP1 VP2 divided by VM2, that is this is the VM2, that is corresponding velocities, ratio of corresponding velocities at corresponding points in prototype as well as model should be same. Then only I can say that it is a kinematic, there exists a kinematic similarity between the prototype and model, that is VP1 divided by VM1, that is equal to VP2 divided by VM2, that should be same, and this ratio is called as the velocity ratio. This is called as the velocity ratio, as here we have shown it. And in the same manner, the acceleration at AP1 divided by acceleration at AM1, that is acceleration at this point divided by acceleration at this point, should be equal to the acceleration at this point divided by acceleration at this point. Then I can say that it is a kinematically similar, and this is called as the acceleration ratio. So this is all about the kinematic similarity. Next, coming to the dynamic similarity, when there exists a dynamic similarity between the model and prototype, if the ratio of corresponding forces acting on the corresponding points should be equal. They should be equal. For example, These are the points which are acting on the prototype at particular point, and these are the forces which are acting on the corresponding points in the model. Then the ratio between FIP divided by FIM is equal to ratio of FVP divided by FIM is equal to ratio of FGP divided by FGM should be equal. This should be equal, and another important thing is their direction, corresponding direction should also be in the same. This is called as the dynamic similarity. Right? That is all about the similarities between the model and prototype. Please subscribe to my channel for further updates. Thank you for listening.